Do you know what pH is? pH is a number that tells us how acidic or basic a solution is. But chemically, pH actually measures the concentration of hydrogen ions. The more hydrogen ions a solution contains, the lower the pH becomes. And the lower the pH, the stronger the acid. Imagine 2 glasses of water. One contains only a few hydrogen ions. The other is crowded with hydrogen ions. Which one is more acidic? Of course, the second one, because acidity depends on hydrogen ion concentration. Hydrogen ion concentrations become insanely tiny, sometimes 0.1 molar, sometimes 0.0000001. Working with these numbers becomes very messy, so scientists invented a shortcut, the logarithm. But logarithms of small numbers become negative. Scientists didn't want pH values to be negative all the time, so they added another negative sign. That's why higher hydrogen concentration creates lower pH. The pH scale usually goes from 0 to 14. 7 is neutral. It is the pH of pure water. Below 7 is acidic. Above 7 is basic. But why does it range from 0 to 14? Pure water naturally breaks apart slightly into ions. In pure water, hydrogen ion concentration equals hydroxide ion concentration, and pH equals pOH equals 7. So pH plus pOH equals 14. So pH becomes 7, and because water chemistry naturally limits most common solutions, the traditional pH scale usually stays between 0 and 14. Surprisingly, pH can become negative. If hydrogen ion concentration becomes greater than 1 mole per liter, the logarithm becomes positive after the negative sign. So ultra-strong acids can actually have negative pH. Not all acids behave the same way. Some acids completely break apart in water. These are called strong acids. Examples of strong acids are hydrochloric acid, sulfuric acid, nitric acid, hydrobromic acid, hydroiodic acid, etc. Examples of weak acids are acetic acid, carbonic acid, phosphoric acid, formic acid, etc. Strong acids ionize almost 100%, so calculating pH becomes easy. But weak acids are different. They ionize only partially. Only a small fraction of them donate hydrogen ions into the solution. Weak acids ionize only a little, so we use Ostwald's dilution law to calculate the pH of them. The formula is Ka equals C times alpha squared divided by 1 minus alpha. Here, Ka means acid dissociation constant, C means concentration of the acid, and alpha means degree of dissociation. A larger Ka means a stronger acid. A smaller Ka means a weaker acid. Suppose hydrochloric acid concentration is 0.01 molar, so the pH is 2. Now let's try acetic acid. It is a weak acid. It dissolves only partially in the solution. Let's suppose that only 2% acetic acid molecules get dissolved, so the value of alpha will be 0.02. And at 25 degrees Celsius, the value of Ka of acetic acid is 1.8 multiplied by 10 inverse 5. So we first calculate hydrogen ion concentration using Ostwald's dilution law. Then after that, use the pH formula like before. So how do we measure pH? There are many ways, like litmus paper, universal indicator paper, liquid pH indicators, pH meter, glass electrode, digital pocket pH testers, fluorescent pH sensors, ISFET pH sensors, and chemical titration. Litmus paper changes color depending on acidity. Blue litmus turns red in acid. Red litmus turns blue in base. Universal indicators show many colors, allowing us to estimate exact pH. For high accuracy, usually a pH meter is used. It's also not entirely true that acids always donate hydrogen ions and bases always donate hydroxide ions in a solution. There are other acid-base theories as well, and we'll explore those in another video. Chemists also use pOH, which measures hydroxide ion concentration, because bases donate hydroxide ions in water solution. But we can also use the pOH term for acids as well. I mentioned earlier that pH plus pOH equals 14. So if we subtract the value of pH from 14, we get the value of pOH. And if we subtract the value of pOH from 14, we get the value of pH. So we can use both pH and pOH for acids and bases simultaneously. pH controls life itself. The pH of your blood must stay between 7.35 to 7.45. Anything below or above that can be deadly for us. Ocean pH affects marine life. Soil pH controls plant growth. Even your skincare products depend on pH. If this video helped you understand pH even a little, then subscribe to the NanoCheMIST and stay with us.